Yes, sir.
Okay. So again, good morning. Welcome to this live interaction session for NPTEL course Interfacial Fluid Mechanics. If any of you have any doubts, please feel free to ask your questions. And today we'll have a slightly curtailed, shorter live interaction session because of some other commitments that I have to be involved in. But yeah, I'm available right now to answer any of your questions, especially from the assignments, if you have any, and lectures. I can see Himanshu there. Himanshu, are you there? Yeah, Himanshu, are you there? Himanshu?
Yes, sir, I can listen, sir.
Yeah, do you have any questions?
Sir, in that, in week 3, so when we were discussing about the contact angle for a sessile drop and the pendant drop, you said that this could be included as a boundary condition so if required, it could be included as a boundary condition for the wall. So I was trying to do that. And I find that my answer is not coming out correctly, because when I put a droplet on that surface, it constantly deforms and forms a flat interface. And
forms a, can you repeat that last bit? And you apply a contact angle boundary condition, and then what happens?
Sir, I am trying to. So we discussed about this, that how to implement. So you said in the lecture that it could be implemented as a boundary condition, which I saw in one paper also when I was referring. So so what I did was I took a droplet and I solved and I put that droplet and solved in the Navier-Stokes equation. So I thought like it would form a sessile drop, but on the surface, on the bottom surface, with the gravity on, it constantly deforms and forms a flat interface. So this was happening, and I don't know whether this is the problem with my code or this is the problem with the implementation of the boundary condition. This thing is going on. It constantly deforms, and so it forms it's just like a layer it forms. So this is happening.
Okay, so well, it's a little difficult for me, as you can imagine. It's a little difficult for me to answer that question because I don't have all the information. I don't have all the data, nor I don't have any direct insight into the kind of code that you're using. Okay, but I'll give you maybe one way to maybe proceed to take the discussion forward is to I'll give you some hints and suggestions with my experience in trying to do these kinds of problems, and you can check. Okay, if that's okay. The first thing I guess is okay. Let me just repeat some of the things that you've said so that others who will watch this later perhaps will also be clear. You're developing a Navier-Stokes solver, which basically you're trying to test this for different problems. And one of the problems that you're trying to test is to basically create a sessile droplet and eventually evolve the solution till it reaches a static shape. And then you can compare it with the solutions that come out of the Young-Laplace equation. Okay, the kind of solutions that we've discussed for some problems. Okay, but as you do these simulations in your code, the droplet continues to evolve, and you start off maybe, I'm guessing, like something like a hemispherical droplet. Hemispherical droplet would mean that it's the droplet initial configuration is part of a sphere, and the initial contact angle is 90 degrees. But the actual equilibrium contact angle may be, let's say, much smaller than that. Okay, or much smaller, much or larger than that. So the droplet is expected to evolve to that state. Okay. Well, okay. So if you have gravity on, okay. Did you check whether the droplet evolves like this irrespective of what value of gravity you use? That's first question. Like as you change the value of gravity, let's say as you decrease the value of gravity, the rate at which the droplet evolves to the final configuration should change. If it is not, that's straight away suggesting that there is something wrong with the code. Okay. The next question, of course, is you have to make the droplet evolve to that state. Okay. So what we have discussed, so far in the course is the static shape, which means that we're asking, I put in a droplet and I ask what is the shape of a droplet which minimizes the overall energy of the system. Okay, we did not answer this question in the course so far. How does a droplet evolve to that state? Meaning the dynamics has not been discussed. Dynamics has not, okay, correct, in week 3. So this is our static shapes. Now if you I'm sorry, if you go from a initial configuration and you want the droplet to evolve towards a static configuration, it's going to do this through some dynamics. Okay. Now this is where the challenge comes in. How do you implement dynamics? For example, I'll give you one suggestion. It depends on how you're implementing the contact line, which is basically the boundary where the droplet touches the plate. That boundary has to move. How have you implemented that contact line motion? Okay, that's not clear to me. Okay, so unless I know that, it's difficult for me to give you a straightaway answer whether is there a problem in the. I mean, I would imagine it's a problem with the code. There has to be either. I mean, when I say code, I mean I'm including how you're implementing the boundary conditions and all of that into the code. I'm not questioning that there could be fundamental issues with the code, like violations of mass conservation or momentum conservation, but it could be as simple as saying that the boundary condition that you're implementing, one is the contact angle boundary condition, but the contact angle boundary condition has to feed into the speed. How are you making the contact line move? Okay, you can use some empirical if your goal is to only reach a static shape. Okay, you can use some empirical velocities for the contact line. For example, one of the empirical velocities you can actually define, and if you can write this down, okay, is to basically say that the velocity of the contact line is proportional to the difference in the angles. Okay, you can make it a little bit more sophisticated in line with some of the models, that the contact line velocity is proportional to the cosine of the angle that is currently present minus the cosine of the final angle. So it will be like cos theta minus cos theta e. Cos theta is the dynamic angle which is changing with time. So eventually when theta approaches theta e, the droplet will, the contact line velocity goes to 0. Okay, so I'm just giving you I'm giving you some hints of how to look at the problem and diagnose the problem.
I'll try this one, cos theta e minus cos theta, because it makes more sense, because the angle on which we are initializing is actually not the correct angle. So the correct angle would be theta e, but we are initializing it with some other angle. So this cos theta e minus cos theta.
Absolutely. The moment there is a discrepancy in the angle, that will propel the droplet to adjust. Will basically the droplet shape has to adjust. Okay, and therefore, in order to reach that final state, we have only looked at the final state and asking what is the shape of that final state. Okay, but if you want to ask how does it go from some arbitrary configuration to that final state, then you are obviously involved in dynamics, which we haven't discussed so far. Dynamics is also there in the course, but it's going to come a little later. Okay, and the last week, week number 12, that's going to come much later. There I specifically discuss a few contact line models, where the contact line models essentially talk about the relationships between the contact angle that is there, the dynamic contact angle, the equilibrium contact angle, and the speed of the contact line. I discussed some of the prominent models or famous models that people have developed over the years. And there are also, these models are not just developed to address the issue of, how do you go from one configuration to another configuration. These models also address another very important issue of a singularity at the contact line, which you will learn about in later weeks of the course. And you can also be mindful of this direction of the velocity. For example, you can make simple hand sketches to figure out, okay, if you have a droplet that starts off at 90 degrees, where the angle is being measured inside the droplet, and the final angle, equilibrium angle is, let's say, 30 degrees. The velocity has to be radially outwards, correct? So if the velocity has to be radially outwards, you figure out what is whether it is cos theta minus cos theta e or cos theta e minus cos theta. I will leave that to you to figure that out.
Sir, so actually, I'm not taking care of this, because radially outward. So till now, what I have done is like we know the curvature. So we have found how to find the curvature. So I have included only that part I have included, and with that, for that curvature, I have already validated this Laplace pressure jump. That is coming out to be correct. But this radially outwards and the direction is, I have not explicitly defined the direction.
Yeah, but so why would the droplet move at all? If you have, how does the droplet know that it has to evolve towards an equilibrium angle and stop after it has reached the equilibrium angle?
I never thought over this.
In fact, I mean, I have in a few years ago, one of my former students, master students, had actually exactly done this problem, and we do evolve and reach the final configuration. In fact, there are lots of other interesting aspects, which is just because a droplet has reached the final configuration doesn't mean it has to immediately stop. It can actually overshoot the position of the contact line, can actually overshoot the final position and come back, relax back again. That depends on the amount of inertia that you have in the system. Okay, so because once you have a velocity, and another thing that you can do is, if it's evolving too fast and your code is becoming unstable, or you're facing other numerical issues, you can actually tone the velocity down by, I mean, these suggestions that I'm giving you are not to basically give you accurate dynamics. The goal is primarily to reach the final configuration. If that is your final goal, then you can actually put in a sort of a pseudo velocity, which means that if your velocity, this cosine of the difference in the angles that I told you, you can multiply it by a prefactor. If it's too slow, you multiply it by a larger prefactor. If it's too fast, then you multiply it by a small prefactor, so that the drop evolves to the final configuration. The droplet has to know, the contact line has to be told that this is not the correct configuration, and you have to reach to a final configuration. Okay, so try this out, and I'll be interested in knowing how this works out.
I'll send a picture of that Laplace precision that is coming out.
Yes, that's the first check that you have to do. The moment you implement curvature and you have surface tension, you have curvature. The first step that you have to do is to ensure that the pressure on the inside and the outside of the droplet, the difference in the pressure inside of the droplet will obviously be higher, and this difference in the pressure should be equal to local curvature times the surface tension. That's the first check that you have to do. This is a test of not only how we've implemented surface tension, but also implemented the curvature algorithm in your code.
Sir, actually, I just wanted to ask this I've been implementing. We had what the equations we had decomposed them in the normal and tangential direction, always, whether it's case of a droplet or a minister. But when we are implementing that, so we are either taking a Cartesian grid, so which is very common and easy to implement, which has x and y direction. And when we want to put it in, let us say, x momentum equation, then sir, so it makes me think over that so sir, actually the directions which we had, normal and tangential, are not in line with this Cartesian coordinate. And when writing x momentum and y momentum, so how do we? It's like so. What I'm doing currently is just to decompose decompose that. So so the curvature, to decompose that, I'm just taking a dot product in the j and I direction. Is this the correct way to do it, or I mean, is there a better way to do this, or this taking dot product is because in the code it is making it itself computationally intensive, because at every point I need to know the x direction for the cell in which I am saying, and if it was in the normal direction directly, then it would have been much more efficient. So is there any way to do it efficiently?
I'm not too sure I fully understand the concern. Also, I'm not a big expert on the numerical aspects of implementing these interface tracking methods. But see, the computation that you're talking about, the computational cost, of course it is high, but remember that it depends on, if it's of course going to be high if you use a fine accurate grid, and it depends on how you're basically defining curvature, how many interface points you're using to define curvature, and so on. But note that you're only doing this for interface points, which is going to be the interface points are basically the cells in your grid, in your computational grid, which have an interface, okay, or that have an interface. Only those cells, only for those cells you're calculating curvature. It is so, and of course, at any given, there are several algorithms, as you will know. If it's a volume of fluid method, then there is again there is a whole range of algorithms that are available. I think PLIC is sort of the most common algorithm. Many commercial solvers, use this, and also many open source solvers like Jeris, Basilisk, they all use PLIC. And locally, what you see is only a straight line in the cell. So the interface normal will be pointing in an arbitrary direction. So yes, when you're solving for the momentum equations involving basically like horizontal and vertical coordinates in a Cartesian grid, then you have to basically, you will eventually have to figure out a way to take the projections of this normal in the horizontal and vertical directions. I don't see a way out of that. But yeah, computational cost should not be as high as, I mean, it depends on what is the accuracy. I don't have a simple way of answering this question because again, high and low are matters of perspective. What is expensive for you may not necessarily be expensive for another person. So I'm not sure I can do a very good job at answering this any better at this point.
I'll actually, sir, prepare one. I mean, I prepare whatever has been, implemented till now. I'll prepare one document of that. I'll send it. So that would be.
Please do email me because this would take the discussion beyond what is the scope of the course. So please do feel free to send me an email, and if I have the expertise to be able to answer you or help you out, I'll be happy to. Otherwise, I will direct you to somebody who knows this quite well.
Thank you so much, sir. Thank you so much. Regarding this, sir, actually, Flick, I have one thing. So I implemented this Flick in my master's during that. So there are another problems which come out, like there are void fractions coming out in the central volume, and how we address the divergence. So it was very, I mean, it's algorithmically very intensive, but so that was there at that time. So that is why I dropped the volume of fluid method.
As I said, already said, I'm no expert on these matters, but there are all of these are basically different ways of implementing. There isn't a correct way as such. These are all approximations, and there are several levels of approximations that one can do, keeping in mind the cost and accuracy in as factors. And every time you basically adopt a certain strategy, I'm sure it will create some other problems which you may have to address it in a different way. It could be Flick, or it could be level set method. It could be phase field modeling to track the interface. I mean, there is a brief description of different kinds of ways in which people actually solve these things. I've discussed that very briefly later in the course. All of these lead to some other unintended consequences, which you will have to address it. I think it's good as young researchers. I think it's good to just keep your mind open to say, okay, all these are different methods, and some of them different methods have different advantages and disadvantages, and you adopt what method works best for you for a given problem. And of course, this is again, that itself sometimes can be a challenge to understand what is the best method. So this is also it's also experiential based learning involved, and this involves experiential based learning because you do something, you try out, it doesn't work, and with experience you sort of get to understand that this is maybe better. Sometimes you get some hints of what is the best method for your particular problem based on what other people in the field have implemented. Yeah, and of course there are other methods also nowadays which are new. Lattice-Boltzmann method is one of them. Okay, but yeah.
Yes, sir. In fact, actually, Lattice-Boltzmann is very promising. I've read some papers there. The best thing about it is like you don't have to find the interface. We can just model that interface using some pseudo potential model they are saying. So it is very it might be game changer in this multi-phase.
Could be. Again, I said, as I'm not a big expert on. I mean, I don't have very limited expertise on the numerical aspects of these problems.
I have no more doubts, sir. I'm complete.
Okay, good to hear that, Himanshu. I would like to sort of have a slightly curtailed session today. I don't see any other students here right now.
Sir, there is one correction. I think it is there. So in the videos in week 3, it is. Sir, in week 3, when you were discussing about the variational, the variation and functional of free surface energy, which is given by delta J, del J.
Okay.
So, sir, could you share that?
Let me share the screen, and you could point to what exactly you're referring to. Let me just share the screen. Do you see calculus of variations of primer? Is this what you're referring to, Himanshu?
Yes, sir. Week 3, sir. Yes. So, sir, in the where you had drawn a hemispherical, and you have shown that there's a perturbation epsilon eta x.
Not sure which one you're referring to.
Sir, above.
Okay, let's start with this. No. This is Euler-Lagrange.
Yes, sir. In here, sir. Euler-Lagrange. So where you draw this half hemispherical droplet with a perturbation epsilon eta x was written after this, sir. After this picture. After
this, it's a state of a meniscus, and then
yes.
I talk about it here. I don't know. Are you referring to?
Yes, sir. Yes, sir. Week 4. Sorry. Week 4. Sorry.
Week 4. Okay. So here's a variational approach to the Young-Laplace equation. Okay. So
sir,
I discuss this and I continue this.
Yes, sir. Here, sir. Here. Here, sir. Please scroll below.
Yeah. Just 1 second. I'm just here.
Sir. So I'll read out the equation. Sir, integral of del f by del h. Integral of del f by del h. Where a little bit above, sir. Above, sir. Integral of del f by del h. Here, sir. Yes, sir. So del J.
I'm guessing you're referring to this, huh?
Yes, sir. The equation written just after this. What you sir, here, sir, you have written del A and del B here only.
Yeah.
Sir, integral of del f by del hx into del hx by del epsilon, where the epsilon, where you have integrated this one, del J.
Yeah.
A little below, sir. A little below. Yes, sir. Here. So it is.
Here we are just saying that this is the variation in the functional, and then if this variation has to go to 0, then either these can go to 0 or this can go to 0. Second half.
Sir, there is one. Sir, there is actually one place where you have written d by dx, del f by del hx into del h by del x, but that should be del h by del epsilon. Second term in the second integral can be simplified to partial differential equation, partial differential integration.
I'm still unable to find which one. This one looks all right to me.
It is actually.
Okay, sir, I think maybe somewhere
here. Here, sir. Yes, sir. So integral a to b is the last term, sir, where your cursor is, sir. So here,
this one.
Negative, right side to that, sir. Okay. So negative of integral a to b d by dx. So sir, it is del h by del x. So you have written. So here, sir, to convert that to del h by del x. So here it should be del h by del epsilon.
Epsilon. There should be an epsilon here.
Yes, am I? Yes, del H by del epsilon.
Okay, just
So
give me a second. I'm just evaluating this. So this is I'm just doing integration by parts. First, the integral of second term. That is, the integral of this essentially becomes, I can integrate out hx. That gives me h. Okay. First term. Okay. Okay. I get it. This should actually be epsilon, correct?
yes.
Okay. So let me just fix that right away. Is that correct? Okay, that's a typo here. Huh?
Yes, sir. It is. It was one more time, but I mean, I think we get the idea here.
Yeah. So this essentially, this entire thing that you see here that I'm highlighting, del h by del x, del h by del epsilon times d epsilon becomes delta h.
Yes, it's now clear.
That
Now clear.
This becomes delta h, right? Yeah. I think this is just a typo here. I think thanks for pointing this out. But it doesn't lead to any other errors.
No, sir. It did not lead to any error.
Yeah, I think this was just a typo. Thanks for correcting that, huh? Pointing that out. But I'm also happy that you've taken the trouble to work out all these things by hand.
Sir, not in the last lecture, but I mean, not the all part, but some part.
Okay.
Actually, sir, I'm doing this for a reason. So there is a purpose that whenever I'm implementing anything, or so in any paper we don't see any derivation. So how intensive it is. So we have done it here. But
yes.
So the problem is, sir, whenever I see something, so whenever we are implementing, so there is no clarity as to where it is coming from. So that is why I'm doing.
Yeah. So that's why I basically, some of these methods for many students who may not have a strong mathematical background, they may not be familiar with the idea of Lagrange multipliers, the idea of energy minimization. Many of them may not have ever heard of. I mean, they may have heard of. Multivariable. They might have used multivariable calculus, but without really ever doing calculus of variations. So that's why I have an independent lecture. Some of these lectures are not necessarily for interfacial fluid mechanics. For example, the lecture on week 3 on calculus of variations, where I basically derive the Euler-Lagrange equations, is independent of this particular course. It could be, it is valid for any course. The first lecture in week 4, the method of Lagrange multipliers. The motivation is, of course, the minimization of energy in interfacial flows, but it is, to be honest, it's valid for a wide variety of problems. So the general method that is independent of specifically to interfacial flows, and that's why this is also reflected in the assignments. There are some questions in the assignments which are of a generic nature, only catering to method of Lagrange multipliers. In fluid mechanics, method of Lagrange multipliers, a lot of students, I mean, any student of fluid mechanics would know, would have used this without sometimes even realizing it. For example, pressure in the pressure term in Navier-Stokes equations is in incompressible Navier-Stokes equations is a Lagrange multiplier. Pressure is basically what is used to ensure that there is an important constraint being satisfied, and that constraint is continuity equation, mass conservation. So that's how pressure basically is a Lagrange multiplier. I wanted to give an introduction to Lagrange multipliers from a mathematical standpoint, and then connect it to interfacial flows. Right. So I think if there are no further questions, then we can end the live session. All right. Thank you for Himanshu. Thank you for attending. Keep your questions coming. I'm very happy to answer them within if it's within my area of expertise, and if, of course, if it's directly connected to the course. And of course, feel if you notice any typos or small errors that the kind that we just pointed out, please ping me or message me, and I'll straight away correct them.
Thank you, sir. Thank you for the correction and week 3 assignment also. Thank you.
Okay. Yeah. Thank you very much. All right. So just ending the live session. All right. Thank you, Himanshu. Bye.
Thank you, sir. Thank you.